Okay, one take. We're doing this. So by the end of this video, we will have built this right here in front of me, the four digit, 7 segment display that is responding to an analog input, which here is a potentiometer, and you can see the number changing as I turn it, which of course you can substitute with a sensor. So basically, by the end of this video, we should have this rat's nest. Organizing your circuits is very important when using this component. But that's all going to go away because we're going to start from scratch. So, and I'm going to put that away and disconnect everything. So we're going to start from the very basics with the single digit 7 segment display. This is what the component should look like in your kit. You'll see the part number is 51618S. By the way, I'm basically doing a walkthrough of a tutorial that is available online at circuitbasics.com. So that link will be posted in the description where this ends up, probably on YouTube. But this is hopefully a little more like interactive and pausable. So this 7 segment display is pretty much how it looks, exactly like how like an old calculator would display numbers. If you zoom in real close, so the 7 segments are just 7 LEDs packed into a box. And then you'll notice this is actually an 8 segment display because that 8th LED is the decimal point. I'll just draw a bigger version of that. So you have 1, 2, 3, 4, 5, 6, and 7. So the convention to designate each segment is with letters. We start with calling, and that's what we'll use to label them throughout this video. So you have A at the top here, and then you start going around clockwise. B, C, D, E, F, and G. And the decimal point over here, we abbreviate it as DP. And that will be used on the pinouts and everything. So it is literally 8 LEDs packed into a box. So let's first kind of quickly remind ourselves how you hook up an LED. We have not been the greatest about using current limiting resistors so far this semester, but here I'm going to hammer on that a little bit more because we do want our circuit to keep running and we don't want to blow out the LED. All right, so an LED, I'll draw the circuit symbol, triangle, and the bar, which right now this is just a diode, and we say it's an LED. We're doing little arrows because it's shining light. And so you would connect the high voltage up here and the low voltage ground down here. So now somewhere in series, the current limiting resistor, well, we need to put it in series with the LED so that it shares the current. And actually, because it's adding resistance to the circuit, it's reducing the current that's flowing through this entire thing. So you can put it before or after the LED. This is showing that the LED is closer to what I'll call V in, which here we'll use as 5V. The LED is between the the resistor is between the LED and ground. But you can also do the resistor before the LED and between, closer to V in. So the way you put 8 of these in a little tiny box is you have 8 of them. I'll draw 1, 2, 3, 4, 5, 6, 7, 8. And what happens is all of them share one side. So reminder, the positive side of the diode of the LED we call the anode. and the negative side we're going to call the cathode. This type of display, that's because we're using a kit, so I'm assuming that everyone's working with this part, um, is called a common cathode 7-segment display, because how it's set up is that with all of these diodes, blah, 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 they all share the same cathode, which is all connected to ground, and each of these now go to individual pins. And each that's how we control each LED and how it's wired. The way this shows up in the component is that if if the decimal point is down here on the lower right, looking down, this component has 10 pins. It doesn't have 10 different connections because 2 of them are ground. So we really have 8 input pins to connect, or 8 outputs from the Arduino to use to control the LEDs, and 2 ground pins. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. On this component, these two, I'm going to use a minus sign instead of writing out ground, just save space. These 2 middle ones are the ground pins. And the way that this is all in the same tutorial, I'm just walking through the graphics. The way that the segments correspond to the pins now is, you remember this order: A, B, C goes down here. Sorry for the mess. This is the decimal point. It roughly corresponds to their locations. And it goes D, E, F, and G. So keep in mind this pinout, which there will be a cleaner copy of it in the tutorial. That is what you will use to connect um, to the Arduino. I'm gonna write out my pin list. I always get confused when wiring this kind of component up that just has a bunch of connections that you have to keep track of. I'm gonna write out my list here. A, B, E, F, G. And so I'm going to connect this to my Arduino. I'm gonna try to connect. Yeah, I'm gonna connect them all in a row, even though like connecting it on a component might might feel weird. Trust me, writing the code will be a lot easier. So I'm gonna start pin A at 9, pin B at 8, and so on. So going down the row. Okay, 3, and 2. And remember, 1 and 0 on your Arduino, on the Uno that we have, are used for serial connections. Do not connect things to it or it will mess up your ability to upload code and stuff. Or at least it will make it very difficult for you to interface with your Arduino. Okay, so let's wire this up. I'm going to figure out all of this. I'll pull up the Fritzing diagram from the tutorial. As we can see here, this is the tutorial here. That's a nicer version of the pinout there. And here is Fritzing diagram. I'll reference my connections that I wrote out are in a slightly different order, but that's okay as long as it shows up in my code like that. If you copy their pinout, if you copy their connections, remember that you also need to change the pin mapping in your program. All right, it's getting dark. Hold on, let me turn on the light. The lighting's weird in here, so I had to turn off the light in order for the LED segments to light up brightly enough. Just plug it in over the bridge in your breadboard. And then I'm going to hook up my ground. have these shorter jumper wires from a different set of parts I have. That's why real-time breadboarding. I'm just going to maximize love the freaking diagram. I'll write this up. Oh, yeah. One tape. I was like gonna challenge myself to get this done in 10 minutes, but I'm already at 10 minutes. I mentioned that this 7-segment display is common cathode, and so if you get a 7-segment display from somewhere else, you might get a common anode display. So actually, so while I have it partially wired up, I'll show actually switch back to DocCam, a quick testing procedure for this. You can see to verify that this is a common cathode display. So I'm actually going to wire a resistor in in series there. Then I'm just going to take a jumper wire, plug it into my 5 volts, and start poking around. I have both of my ground wires hooked up, and then the resistor is meeting them, and then the resistor goes to ground. So these are not directly connected to ground; they have to go through the resistor. So if I start poking at the pins, you can see that I light up the segments one by one. And you can actually verify the pinout if you ever get confused. But that is also what taking notes for. So I'm going to wire up the rest of the connections. I said so A. Here is this one. And that's going to go to 9. You can see. So I do have a program running on the Arduino. So my light's going to be kind of all over the place. And it goes to C. Yeah, kind of everything's lining up because this is running different code than it's meant to be doing. This is going to be long. Okay, 1, 2, 3, 5, 6. The good thing about this kind of component is that if you mix up the wiring, as long as the ground, so as long as your ground's in the right place, you're probably not going to blow it up. But if you do have any of these input or the Arduino output pins switched around, you'll know immediately because your output's all garbled and does not look like actual numbers. That's G. And then I need the decimal point pin 2. All right, well, we can at least see that all of the segments are lighting up. Yours probably is not going to light up because unless you have code running on your Arduino that uses all of those pins already. But anyway, so let's get programming this. That's breadboarding for now. Again, pay attention that you have the current limiting resistor in the right place. Both of the ground pins should go to the same row. And then the resistor, this is a 1 kiloohm resistor. Sorry, I forgot to mention that. The resistor goes between the row that the ground pins are connected to and then your ground rail or a separate, wherever else you have the ground from the Arduino plugged in. That way your display is not directly connected to the Arduino's ground. It has to go in series through the resistor first. All right. So we are going to open up a new Arduino program. And there we go. All right. Okay, I'm going to code this from scratch. It's going to seem super, super, super tedious. But that is, and it's going to be really inefficient. But I want you to follow along so we can directly work with some of the nuts and bolts of the mechanics of the LED display, because this is literally just controlling the LEDs one by one. So for now, we're going to pretend like we're controlling a set of 8 LEDs. So later we want to use a library, which will save us time, but we're going to just define first all of our segments. So segment A went to pin 9, and this is going right back to the pin list that I wrote out. So seg B goes to 8, goes to 7, goes to D, goes to 6, E goes to 5, F goes to 4, G goes to 3, and then decimal point DP goes to 2. All right. And then we're going to define an array just to make things a little simpler for us. An array of the segment pins. I always get this mixed up. When you're declaring an array in Arduino, it will, so if you're, there are a couple different ways. We're making an array by, is it direct assignment? Shoot, I forget the term. Anyway, so you can create the array with the values already populated by using curly braces and then listing out the numbers. So we're going to put in the names that we defined to make our code readable. I'm just listing out all of our segments, and you'll see why, because we want to kind of like set them all in a single like workflow. So those are 8 segments. And then because we're controlling these like just simple LEDs, we need to set them all as outputs. Normally we would just do pin mode, pin number, X output. But this would be really tedious. I don't want to write out 8 different pin mode statements, so this is why I created the array. So I'm going to do a for loop for int I equals 0, I is less than 8, and we'll go iterate through I plus plus. So for each I, for each index, we're going to do pin mode segment pins at I. Sorry, my docam cable's in the way. Pins I will be output. So we're just going through that list of pins, and they're all going to be outputs. And then for we can actually do just a simple little thing where we kind of keep cycling through these pins in a for loop. Let's say when we first did that, we would do digital write. We would just set all of the pins high and light them up just to see if they're all working. And then when we get into the loop, you can do more for loops. and so on. Actually, okay. Let's come back to the loop for a bit. So we can see here, we can just directly write to the pins to set them high or low to light them up. So let's just kind of dissect the logic of the 7-segment display a little and think for a moment how we're used to these numbers looking. We're just going to manually build up a couple of numbers just again to get an idea of how this works. Then we'll bring in the library, which does things more automatically. But let's think about 0. On the 7-segment display, how we would display a 0. Pause here if you want to think about it. And I'm just going to tell the answer. So we would light up all of these outside ones. A, B, C, D, E, F. G would be off. So one way to code that would be another array. Let's do, I'm going to call this display 0. It's an int array. I know, again, we're being inefficient here. We're just doing the most readable things that are available to us. I'm going to do a little format comment where we're going to put each of these values, A, B, C, D. So like we said, to display a 0, we'd have to turn on A, B, C, D, E, F, turn G off, and we'd leave the decimal point off. Now what about 1? The numeral 1. We could take either the left side or right side, but the convention is to light up the right side, just so it looks nicer next to the decimal point. So that would be segments B and C. So if we are coding display 1, that would look like everything's off except B and C. If you've ever done kind of like very low level like microprocessor circuits, this would be we're basically making a truth table here. So let's write out just one more. How would we display 2? Let's look again. I'm a very visual person. This just helps me like break down what's going on. So 2 looks like a zigzag. We'd go A, B, G, E, D. A, B, G, E, D. So the array, in the truth table, that would look like 1, A, B, G. So C is off, D is on, E and F are off. Wait, no, E is on, sorry. And G is on, and decimal point is all off. All right, I'm sick of this. We're just going to now, we have 0, 1, and 2. We're just going to make a silly little program that cycles through 0, 1, and 2. So let's start a counter, 0, and in our loop function, all right, so again, we could do a for loop, int I equals 0, cycle through all 8 pins, I++. We'll do digital write. And now that we have arrays for both the segment pins and the actual figure that we want to display, this is also showing you how to code like a custom character, because the standard character set doesn't come with all, I don't even know what combination, however many combinations, configurations of LEDs you could light up. But anyway, so let's say we wanted to display a 0, we can just plug in the display 0 array, and this would write 0. We can get a little fancier than this to cycle through. So we could do, say, we want to display the value of the counter, and the counter is going to be cycling between 0, 1, 2, 0, 1, 2. Could do an if statement, then else if, and then else. For just some variety, and to if this logic structure is new for anyone, we'll just go over it real quick for the Arduino language. There is the switch case structure, which if you would be doing a bunch of if-else statements on an integer, you can also do a character because those reduce to integers between 0 and 255. This can make your code look a lot cleaner. So we're going to do, and what basically this is going to look like is we're going to switch the variable that we make our decision on is in the parentheses, which we're going to make our decision based on counter, and then open some curly braces. And this is all going to indent. And when the way we make our cases then, instead of if and else, so now we have a switch, we can define cases. So in the case that counter is 0, we would write case 0 colon, and now all of this code would execute. And you notice the case is not opened with a curly brace. Instead, so we don't close it with the curly brace. Instead, what we do is the last line of each case before it goes on to the next one, you do break. So in case 0, then it would execute this for loop to display 0 and then break. If you didn't put the break, it would actually just kind of go through and execute all the cases in a row. So for case 1, which has to go after the break, we could do a different for loop. I'll just copy and paste this. Of course. Okay, so if you've been following along and you get the idea, go ahead and just like skip forward. That's the advantage of pre-recording these things. And also me trying to plan for this kind of format. So to display 1, we create a new case and make a new for loop to display the 1 array, and then we break. And then case 2, same thing, except we're now displaying 2, and then break. And then this is not required for a switch case structure, but as a safety measure, and I think it's a good catch-all, this is the equivalent to else. You want a default. So if counter is not in any of these cases, 0, 1, or 2, then we just want to create like a safety measure. So maybe if the counter is not, it is something unexpected, then we just display the decimal point. So let's do that. For so for int I, so actually that would be all the last one are low, and then we would digital write the last pin to be the decimal point to be high. All right, so that's all the counter, and now we need to actually change it up. So, well, counter needs to be changing. So we're going to increment counter at the end of all that logic. To make it loop around, we could do counter is equal to counter modulo, I just spaced, counter modulo 3. And then because this will execute really quickly, let's stick in a delay of a second. We'll see if we could upload it. I need to save it. Right. So we should see, hey, there we go. 0, 1, 2. All right, that was really annoying. I don't want to do that anymore. So we're going to now open up a, we're going to find a library that does this for us. So very fortunately, Arduino actually has a very well done library that works with the 7-segment display. It's called SevSeg, and I don't think it's in the library manager. You can look in it, but with the tutorial wrapped up with all the materials, we have a zip file, and so you have to download the zip, save it in a reasonable place, and then if you once you have it downloaded and saved, then you would go into Arduino and we would go to include library. Add the zip library, find it where you saved it. I already have it. So once it's included by adding that zip, then you should be able to scroll all the way down and you'll see SevSeg. So you should be able to now, once you have it, this is now available to you for you to include. You just open up notes. All right, so the way this works, and again, you also have the tutorial to refer to for their code, and all of this references it. So I am going to cite that in my code. Using multi-line code based on example from that page. Again, good practice just to be a good citizen of the open source community. Give credit where credit's due. And so we include SevSeg, then we now have a different class available to us. A lot of this will go away. I will clean up the code later. I'm going to keep my segment pins array because that is actually useful. That wasn't in their example. I'll keep the format for now. But now we can declare a SevSeg 7-segment. Pay attention to the capitalization in the middle. We can declare SevSeg as an object. We do want that segment pins, but it actually would prefer us to use bytes. Notice that, yeah, we could. The people who are very into bit managing, you've probably noticed that, oh, we have 8 pins that we are writing to. We could just store all those values as a byte, and we would shrink our data usage by a lot, our memory usage by a lot. But once we have this object available, we don't need anything because the SevSeg library comes with all of those values already, just coded up for you. So instead what we need to declare num digits. You'll see later we'll come back to that to get the multi-digit things. And then there are some parameters. Hardware config. This library can handle other kinds of segment displays, so we do need to just specify we're using a common cathode display. And then for all this, we don't need any of that. And we can just sevseg.begin hardware config num digits digit Oh, yeah. So we do need to declare digit pins, but we only have one. We're only using a single digit one, so we actually don't create an empty array for digit pins. Digit pins, and then our segment pins. And resistors on segments, yes. So it takes care of all of that for us. It's a few parameters to remember, but it's worth it because now in our loop function, we can just get rid of all of that. And now we could do anything with our counter. Well, we could display all the digits with the counter now. So if counter could just keep going to 10, well, it's from 0 to 9. And instead of all of that logic, we simply just need this line. It's beautiful. Set the segment display to the counter value, set it to a number, and then refresh the display. One thing about SevSeg is that the refresh display function needs to be called every loop. So whatever, if your counter is not updating every loop, which usually it won't be, whatever like logic is updating counter, refresh display should be outside of it, probably like as the very first line or as the very last line of your loop. Yeah, I think that's it. Beautiful. Oh man, it's only almost 40 minutes. Oh, God. Could I just like speed this up by 1.5 times? I don't know. All right. So it uploaded. And now we see we're going above 2. All the way to 7, 8, 9. And then we should loop back around. When the display goes out of range on its number, so when you have 1 digits, if you go to 10 or above, it'll just display a dash, the middle segment. So yeah, that is the single segment one. So, okay, we're going to do more digits. Okay, so all of this was a lot of wires. So I don't know, you might be concerned that, well, if you have 4 digits, you need like 4 times as many wires. We needed 8 wires for the single digit. So do we need 8 times 4, 32 wires? Luckily, no. Through some very clever engineering, and of course, I have a wire that broke. Uh, through some very clever circuitry, we actually only need 4 additional pins to control all of these um, digits. So the single digit had eight, eight controller pins, and the 4-digit display has 12. Keep in mind, your Arduino Uno, 12 digital outputs. So 12 digital outputs and 1 and 0, which you should not use. So this, if you are using the 4-digit display with your Uno for your project, you can't really have anything else digital like a button in your system. You can have analog things. You can have 6 analog inputs, and you could still have it talking to processing, but you can't hook up any other digital inputs or outputs. Okay, so I'm gonna unplug my single digits, hopefully without breaking everything. move it over to here. So let me introduce first. Actually, this is convenient because these are the wires that were left when I pulled out the LED control wires. So the four additional wires that the four-digit display adds are the digit select pins. We have four additional wires going to um, each digit. So the way that we select, basically what can happen is um, all of all of the LEDs are still wired up pretty much the same, and they all overlap and share. And so, let me draw another diagram. When two, three, four, um, poof, basically, yeah. Each of these digits has their own A and their own B. I'm not going to draw all of them out. Let's do that. C, D, and so on. Each segment has its own, has connections to all four digits. And what happens is now we have digit select pins. DS, and we have DS is a 0. Really? They start counting at 1? Okay. Well, they number them 1, 2, 3, and 4. So each of these, you'll notice, instead of ground, um, is there are no ground connections in with the four digit display. The digit pins, what happens is they serve as ground when they activate that digit. When that digit should not be lighting up, it actually goes high, which means that there's now no voltage difference across the LEDs on that digit, and it doesn't light up. And it's pretty clever. Okay, let me pull up. This is a cleaner diagram of what I was talking about. You can see, yep, all of those connections, but you only have 12 things to worry about connecting. So here is the pinout for the four-digit display. Pay attention to, and what's tricky about this is like once you plug it in, it's hard to see pins. So if you like really tilt it up, you can see where the pins are. And then I would just like pick one in the corner so you have it as a reference. The lower right corner, that's the pin for digit 1, and then you connect it to a, then you would connect that D1 pin to the resistor, then to ground. So I'm going to start wiring that up and scroll down to the Fritzing diagram, and I will see you on the other side. If you capture wires from the first segment, the single digit display intact, then you should be able to keep them in the same order. What I'm going to do is I'm going to connect D1 to 13, D2 12, D3 to 11, and D4 to 10. It's pretty satisfying to see all of those pins um, hooked up, but it's also like, man, you really can't do anything else. All right, and then similar to the single digit display, we have the pins for A, B, C, and so on. But they're in a different order, so I really just have to keep referring going back to the pinout. So I'm going to start A that goes next to D4. B all the way. Oops. Is there a way I can show both? Nope. Okay. I don't find the Fritzing diagram all that useful because it's so messy. You can pause on it or go back and pause on it if the Fritzing diagram is more useful to you. I'm hooking up C and B. E, F, G, and DB. All right. That's not too bad looking. Okay. Hopefully I got everything correct. Again, if you're not sure that you got all the wires connected in the right order, as long as everything's hooked up in the right polarity, like you didn't mix up your ground and high voltage, then nothing should blow up. If you Once you just start running displays on it, then you'll just see that the segments are mixed up, and you can hopefully that's some built-in troubleshooting right there. All right, so we're gonna go back to coding now, and we're going to turn up the number of digits here. So we now have 4. Num digits is 4. We're going to list digit pins. It's 10, 11, 12, 13. For some reason, it lists from 4, 3, 2, 1. I'm not really sure why. That was a design choice. And I'm also going to do an additional I'm going to do an additional Boolean to disable the decimal point. You can display decimal points now that we have all 4 numbers. You can display 3.145 or pi. You can display whole words now, which is nice. So we edit that. This is something that we didn't do in the earlier example, but now we're going to add in a brightness setting. So brightness goes from -100 to 100, which is weird. But really, you don't need to worry about the negative numbers. It's a way of managing like delays and stuff. So you can do 90. You can go all the way up to 100. I'm gonna do 100 because the lighting's weird here. And so now we set the counter. We should be able to let the counter just do anything, right? So how about this? Let's take out this delay for now, and let's just see how fast it counts. Right. Okay. Yeah, there we go. Oh God, it's dark. You can see um it counts up very rapidly, and then once it gets to 10,000, then it just flatlines out. So yeah, that's what happens. It's just showing that the value is out of range. So what if we want to slow down this count? Well, we could put that delay back in. I'm like looking like a ghost in this preview now. Yeah, but it's going to look weird. Why? Skipping. And it's actually, yeah, it's not displaying well. Sorry. Let's see. So yeah, skipping numbers is only like showing one digit at a time. So what's happening is that delay is really messing with things. Refresh display doesn't quite work with timer. Like time, well, so what, and this is showing like why delay is generally bad in Arduino programming actually. We use it as a quick and dirty way to introduce time into like and just like time waiting for in our programs. But what delay does is it actually, the Arduino will hang everything else that it's doing and wait for that delay to finish. What we want to do is not have this delay command because the Arduino is executing these lines one by one and it's not going to leave the delay until it's finished. So what I'm going to introduce to you is the millis function. I don't believe we've used it before. So we're going to, we're going to fix our counter. We still want it incrementing every second. But because we now have a more complex display, we should not be using these delays. I'm just going to get rid of that. And we need to use millis. So what the millis function does is it's the Arduino just using its own internal clock to spit out a number representing a just a timestamp in milliseconds of when that check occurred. When did it look at its clock? This is only an internal clock. It's not synced up to any external clocks. For that, you have to do some of the time and web connectivity that we talked about in lecture. But for now, we just want internal time. It's fine. Millis is weird in that it uses, well, because it's a really big number, it actually uses a different number format, which is called long. So we're going to do long time. No, not time. Where you want to store kind of like when it last checked the time. So we're going to declare a long previous time. And then in the loop, we'll declare a different long called current time or new time. And that we will read millis at the moment. We do need to actually start preview time. So in the beginning, right after setup, that's when we'll start the clock. So preview time is going to be equal to millis. And then when we start going into the loop, then we take a new millis reading. What we can do now is we have that checkpoint at some time in the past, and then we have an idea of how much time has elapsed since then. So now what we can do is we can take a difference of that time. So if new time minus preview time is greater than 1,000 or whatever our update speed is, then we would execute code that involves updating everything. So that's when we would want to update the counter. And again, I'll take out refresh display because that needs to happen every loop, or things will look really weird and flickery. So if doesn't hurt to be setting the display every cycle, but we don't want counter to update every cycle. So now counter updating is only in that if statement, and that's only when the difference between now and the last time we checked the time is 1,000 milliseconds a second. So now once we've updated the counter, then we can just shift over. So now we want to start counting from this new time that we just took. And that's it. So let's see if that works in it. This is always the awkward part. I had to wait for code to compile. Done uploading. And now it's back to counting at normal. Yay. All right, well now we have a built-in timer. And from here you can do like a simple, you have your buzzer, you could do a simple like kitchen timer, a really over-engineered kitchen timer, but that's something. So just one last thing, I am getting tired. It has almost been an hour on this video. We're gonna do one last thing, and we're gonna hook up the potentiometer for, so that this isn't just displaying a counter, it is displaying a reading from an analog input, which we're using a potentiometer to mock up. So you remember how the potentiometer is wired? You need more jumper wires. All right. In the middle pin, we'll go to an analog input, and then take your pick. One end goes to ground, and the other end goes to 5 volts. Then we need to modify our code. We don't need to configure an analog input pin, but now instead of counter plus plus, and we probably want to check the potentiometer more frequently than once a second. So let's decrease this update frequency to 100 milliseconds, a tenth of, so it'll update 10 times a second. That's plenty fast. Instead of counter plus plus, we can do, I guess, yeah, counter. Well, let's change counter. It doesn't make as much sense. Counter is going to instead say sensor reading. And sensor reading is going to equal analog read. I plugged my potentiometer into A0. We update the time. All right. So yeah, I have the thing where my potentiometer is a little wonky and doesn't like to stay in the breadboard, so I have to hold it down. But now we're back to the potentiometer controlling the input. So you can display, see, all the way to 1023, and then when I twist it the other way, all the way down to 0. All right. one last fun thing. Let me show you what it looks like when you display characters. Yeah, so the dock cam does not like low light, if that makes sense. All right. So let's say you can display, again, 4-letter words here. Not all the 4-letter words, because 7-segment displays are limited in the letters they can produce, and you have to format things a little weirdly. So if you're curious exactly for more details, what kind of characters you can display, what you want to do is go into, you can look at the source code for more information, but you can see the entire character set. You can do dashes, degrees. Okay, so some of these are not, and like some 7-segment displays have like the extra pips that can display other things. You can see here, K is going to show up like H because there are no diagonals. It can't do W or M. And some like lowercase looks better than the other. So it's like when you were typing like stupid things on a calculator at school. We're going to modify this code to, let's say we wanted a warning if the sensor value went too high. Where is this one? I have too many Arduino windows open. All right, so if sensor reading is maybe like, say, above 800, if that meant like the temperature was too high or something, then instead of setting it to sensor reading, we could do SevSeg.set chars, characters, and you input a string here. So we could do nope. That would work. And then in the else statement, we can just move the set number. So if the value is okay, then we can just set it to the sensor reading. Now let's update that. At least its focus is decent. All right, so I'm at 70 something. I keep turning it up and up and up and up and up. Getting close. All right, now we just display nope when we're above 800. All right, so that was a really long video. That turned out way longer than I thought it would. But that is how to use a single-digit 7-segment display, a 4-digit 7-segment display, and also how to, display numbers, control the data inputs to it, and even display some words. All right, hope that helped, and hopefully I get everything in the description. Oh God.